continue with the lecture. First lecture in the series of Slovák, Cartan geometry via Algebra. So, please.
Yes, usually the people thank to the organizers for the invitation, so I feel sort of stupid that I'm presenting the lecture myself, but in the time we were preparing this training school, I was rather thinking in the terms of training, and I found it difficult to convince many people to go for some series of training lectures, so I thought that it would be fine if I do one myself. So now I don't think it's that much fine, but I will give it a try. And the goal of my lecture is to, well, you have seen the title, Cartan geometry via algebra. So we wanted to, it's our collaborators, so I can at least thank my collaborators, Jordan and Katarina, for preparing this series. And we were discussing how to split it in a reasonably complementary way. So we had Boris presenting the original exterior calculus approach. We saw Rod going more via the tractors and this kind of nice stuff. Now we had Jordan showing us what were the roots of seeing these as useful things in physics, and I will try to make it as much algebraic as possible. And the main reason for that is that it's a first week before the second one where we shall have the commutative, non-commutative versions of the classical geometry. And there, the typical approach at the beginning of everything is just to see what's happening in the classical situation, but in the most possible algebraic way. So instead of points in a manifold, we have the algebra of smooth functions, etc. And so I thought it would be a good opportunity to go back to a very old, well, relatively old paper of Mike Eastwood and myself, where we tried to do something along these lines, and we tried to generalize the approach, how to understand the invariant linear differential operators for various kinds of geometries, which is normally done via the representation theory and the structure theory of Fermat modules and all these kind of things. And we try to find the right analog for that in the curved setup, so going from Klein to Cartan. And in some sense we succeeded, and we sold it to Journal of Algebra, so you see it was very algebraic. But otherwise, whatever I will be talking about can be more or less found, at least at the level of the Cartan geometries themselves, in the first chapter, the fifth part of the first chapter in our parabolic geometries book with Andreas Chapp. And also I thought I would be much more concrete here and base everything on examples, because we came back to that story with Vladimir Souček, and we are trying to understand some particular geometries more deeply than we did with Mike in this semi-Fermat modules paper. But unfortunately we were not so efficient. Yeah, efficient is the right word, during summer, and so I can't talk about any results yet. But it's a forthcoming project with Vladimir Souček, so I should have mentioned him. Right. The plan of the talk is, in the first lecture I should like to explain the basics about the jets and induced modules. And then I shall continue in 2 days, and that will be a try to explain the translation principles. Let me see. Oh, I will put the plural there in bracket, and then in the last day, if there will be time left, if I go through all that, there will be some examples. Also depend how much wine we shall drink on Thursday. Right, so that's the general plan, and let's now come back to the theory. So, I mean, the general background is the motivation goes back as far as to the Klein's Erlangen program. So Felix Klein. So I will just start with some comments on Klein's and Cartan's worlds. So perhaps it has been already told too many times here, but I will do it again. A Klein space means that we take a Lie group G, Lie group, and we take a subalgebra. I will call it P, although I have no requirements yet for G and P to be semi-simple, parabolic, or anything else. Just P is a closed subgroup in the Lie group G. Everything will be finite dimensional for me. And of course, then we've got the principal fiber bundle. Let's write it pi G to G mod P. And I will call this M. That's the homogeneous space. And of course, we have seen already that there is Maurer-Cartan form on the Lie group G, which is just the one form which tells us what are the values of the left invariant vector fields having the right thing in the origin. So it's the trivialization of the tangent bundle of the Lie group. So it goes to Lie algebra of G. So it's the Maurer-Cartan form. And we've got the structure equations. And the structure equations say that d of omega plus 1/2 of the bracket omega omega equals, and because it's the Lie group, so we know it equals to 0. So in this sense, the Maurer-Cartan form encodes the multiplication of the man on the Lie group in the infinitesimal way. Right. So how does it look for the Cartan? So this is Klein. For Cartan, we have also seen it here several times. So and Felix Klein would call this just the space. So the French people call it espace. And Cartan talks about generalized space. And the general idea of Klein was that actually to do some proper analysis which would be useful, doesn't matter whether for engineering or physics or elsewhere, there always should be some expected either seen or hidden symmetries, so symmetries which would integrate to some real transformations you want to preserve, or which are expected at the infinitesimal level. And therefore he thought that instead of doing all the analysis as we teach our freshmen in Rn, it should rather be on a homogeneous space. And all the objects we want to deal with should be invariant with respect to the action of the group G, because the left multiplication on G, of course, is then seen via the projection as the left multiplication on the homogeneous space, and there is a transitive action, and P is the isotropic group of the origin. So the projection of the unit of E is what we call the origin. Right? I will call it O. And so Klein coined the idea that all our analysis should be rather performed on such homogeneous spaces, and the choice of the Lie groups should correspond to the aims of our analytical tools and everything. And that's exactly what the people are coming back now to in geometric science of information, as we saw last week, and in all the deep learning methods and in statistics and all these kind of things. So somehow it looks like this is becoming fashionable again. And I will mainly talk about the client's world today, but not only. So, and what's the espace généralisé by Cartan? So he actually didn't write it exactly this way, because the principal fiber bundles were not ready as language, but he was trying to understand some given geometries, as say CR or Riemannian or the Grassmannian kinds we saw yesterday in many of the lectures, in a way which would mimic the client's approach as much as possible. And so in current language we can say that the Cartan's version is, we have got a G is a principal fiber bundle, so it's over M, it's a principal fiber bundle. P is the structure group. G is the structure group of the principal fiber bundle. And instead of having the Maurer-Cartan form, we simply choose some one form, so it's a absolute parallelism, and this absolute parallelism satisfies all the other conditions, all the other properties of the Maurer-Cartan form, which still make sense. So we want here if we take any element in the Lie algebra, so the inverse image is what we call there the left invariant vector field. So here we shall also have the constant, so-called constant vector fields omega inverse of some given element x in the Lie algebra. So that's what really works exactly as here. The other two properties have to be restricted to the structure group only, because there is no left multiplication. So we want to have the one form, Lie algebra valued one form, we want to have it equivariant with respect to the adjoint representation, and we want to have it, we want to reproduce the only analogy we've got here to the left invariant vector fields, and that's the fundamental field, vector fields, right? Reproduces fundamental vector fields. And of course, then this Maurer-Cartan equation is no more true, and instead we get the omega plus 1/2 of omega omega. That will be a 2 form on the total bundle G, and we call it the curvature. That's the curvature. And this is Cartan's world. Oh. And you can imagine really that it's a deformation approximating somehow infinitesimally at each point the Klein geometry. And actually Cartan in some sense did it this way. So if you go back, for example, to his famous paper where he resolved Poincaré's description that the three-dimensional CR structures in C2 can't be CR isomorphic to the round sphere. And Poincaré did it by just claiming that if you look at the biholomorphisms, it's much smaller category of morphisms that the freedom in building the hypersurfaces in C2. And therefore it can't be true, but it was not a real proof in our sense, whereas Cartan simply did osculation of the three-dimensional hypersurface at each point by the round sphere as good as possible with some normalization. So it was very much along the talks yesterday, in particular Misha's talk. And as a result, he got exactly to this with the structure groups we heard yesterday. So that's how it works. Now let's come back to what would be the objects helping us with any kind of analysis in the Klein's world. So what we would deal with is not functions, not tensors, as they are usually taught for the freshman, but we would talk about a homogeneous bundle. I'm sorry, I'm perhaps too elementary for most of the people here, but I promise to be really very elementary for those who are not yet familiar with the things, although I mean those I had in mind were here yesterday but didn't come already. But I hope you will not be too angry with me. So homogeneous bundles, what does it mean? So usually we are used to work with vector bundles over manifolds. So if we are on a Klein geometry, we want to have vector bundles where the action of the group on the base manifold M would be covered by an action on the fiber bundles, right? And all such homogeneous vector bundles come to the world by, well, essentially all come to the world by looking at the structure group of this principal fiber bundle. So if we have, say, a P representation, so lambda will be a representation of P to say hom or automorph, yeah, so why not? V for some V, or maybe I will just write V lambda will be a V module, it will be a P module, and lambda is just the homomorphism from P into the group of all automorphisms in GL of the space V. So this is blackboard mode V, right? And of course what we can do is we can build the associate bundles. Bundle, I will write a V, polygraphic V, and this will be G cross over P times V. So it means that we actually take couples, a frame U in G, a general element, and a V in the module V. So this is an element of G cross V, and we say that this one is equivalent to U times, say, G minus 1 dot V. So this is just a lambda G minus 1 V, right? So this is something everybody should know from, say, the third week of the first semester of study. because that's the way how you build your vector bundles, right? So of course, usually the beginners do not think that a vector is a mapping from basis to coordinates. But if you think properly, that's what they should, right? Because that's completely invariant. And so instead of talking about n-tuples, you should say that the n-tuples are given by the choice of the base. And if you change the base by multiplying from the right with the matrix G, then you have to multiply the coordinates from left with the matrix G inverse. And that's it, right? So these are the associate bundles. And actually it's a functor which eats P modules and produces vector bundles. And on those vector bundles, of course, you have the left action by the group G, because you simply act on G. So if you act on the frame, it's commutative with the right actions by the change of the frames, so nothing changes and it's well defined, right? So these are the homogeneous bundles. And of course, if you now take the sections of V, so space of sections, so these should be the objects of our interest. So that should be the objects where we want to do all these operations in an invariant way. And of course, on the space of sections, we again have got the canonical action of the group G. And what is the action? So actually, the sections can be viewed as mappings S from G to V, having the property that S in U times G equals G minus 1 acting on S at U. Of course, we know that whenever we have something like that at the level of Lie groups, then we can have the same thing at the level of Lie algebras. So at the level of Lie algebras, it would mean that if we consequently, if we say differentiate with a Z, so this will be in P. So that's the Lie algebra of the subgroup, and omega inverse of that is the fundamental vector field. Right here, it's the left invariant vector field. And if we differentiate S, then it will be minus the action of Z at S. Right, that's more or less obvious, isn't it? It's just from the...
I have a question.
Yes?
I'm sorry. So when you say this functor, what does it do to morphism? More precisely, which morphism?
Morphisms are the left actions of the group elements.
Yeah, I was wondering, the base stays the same under this
Yes.
morphism. Okay, thank you.
Yes. Yeah, that's the functor which takes the base manifolds. Well, actually, it takes. Well, you can take it both ways. So you can
Right.
say that if you fix your P module, then you have functor which associates to the homogeneous space all the vector bundles, right? If you take it as a functor from modules to Klein geometry, to the homogeneous bundles, then it means you have fixed the
Yeah, my
Klein
worry
model.
was about the morphisms, because if you want like an equivalence, you're not going to get it because the morphism of bundles, maybe there are more. That's all. But okay, it was just thinking.
No, it's the functor which produces you the homogeneous bundles. So it's the bundles with the action of the Lie group.
Yeah.
And then you of course want to have the actions of the Lie group which
Yeah.
is...
No, it's clear. Thank you.
So this is now the homogeneous bundles, and so these are the sections, and what is now the action of the Lie group on the sections? So the action of G on gamma D, if we view the sections as these maps, is given by composing with the left multiplication with the inverse. So G acting on S equals S composed with this guy. Right, so that's quite nice to know from the beginning. And what about now? So that's the homogeneous bundles, and tomorrow we shall come to constructing the algebraic nice gadgets which will be helpful in dealing with operators which eat sections of the bundles and are invariant with respect to such action. Before going there, let's have a look. What does it do for the Cartan geometries? Cartan. And there, it's exactly the same, except the same construction. Except there is no G action there anymore. Except we deal with morphisms going from G to G tilde or G dash, say, preserving omega 1. Actually, I would want phi star omega dash equals omega. So what I mean by that is you take principal fiber bundle morphisms. The bundles are equipped with the Cartan connections. It's one form, so you can take the pullback of the one form and you request that it's this, right? I wouldn't say it's an easy homework or exercise, but it's possible to show that actually the space of automorphisms of one such bundle, that means those which keep the Cartan connection intact, is a finite dimensional Lie group, and it's never bigger than the group here. Whereas for the Klein geometry, you can show that this definition reveals that all the homomorphisms are exactly the left multiplications, right? As I shall not go into any details here, but otherwise, whatever we had here makes sense again. So the functor on the functor on the P modules, which here worked on the homogeneous space associating the vector bundles, which are the homogeneous bundles, now produces the associate bundles. V at M would be the fiber bundle. G, so principal fiber bundle G, again the product over P times V. The sections are again viewed the same way, and consequently again this will hold true. And in particular we can see for the curvature particular, so the K equals d omega plus 1/2 omega. Omega is actually valued in omega to m, and here will be something I will write a m for the adjoint representation G. So there is the adjoint representation of the Lie group G on the Lie algebra, small g, fact G, and because of preserving the fundamental vector fields, which we requested here, so we know that actually this curvature K disappears whenever one of the arguments would be vertical, and therefore it descends down to the manifold M, and there it would be a two-form valued in what we call adjoint Tractor bundles, right? So this is the adjoint Tractor bundle. Right. So let's have a very simple example. And the very simple example would be what happens if G is the affine group, or is, well, why not? Affine group and R. So it means, as we saw yesterday, everybody showed the nice matrix plot. So you have this kind of thing. So the algebra has got zeros here. Here is Rn, and here is GLN. So that's the Lie algebra. And the action is here, right? And what is the Cartan connection of that type? Yeah, we say that the Cartan geometry is actually modeled over the homogeneous space G mod P. So the Cartan geometry is omega is, because here you see it's a reductive case. So the subspace Rn is invariant with respect to the action of the GLN, and therefore you can split the Cartan connection in two parts in a natural way, and it will be the so-called soldering form, which simply shows how the Lie group G acts as frame bundle over the quotient space, which is the Rn. And then there is, say, some gamma. This will be this part of the Cartan connection. And this is a linear connection on the manifold. And the only difference to what usually people learn in the basic elementary classes is that we stick to having them always together. And of course, d omega then produces the torsion and the curvature, right, in that particular case. If you have any subgroup of the affine group, then the Cartan connection, it means you have got a affine connection, so linear connection of the manifold, with the special holonomy in the subgroup in the GLN you take, right? So if we just take a reduction of the whole GLN. So that's the example. And let me now go on a little bit to show how this sort of algebraic approach and calculus works. And we may, yes, so the first thing to understand is that the curvature, as I claimed now, is a two-form on the manifold. So it should be one of the cases of the sections here. So how shall we get there? And the way how to get there, the curvature function is obtained in such a way that you take k kappa. So now it's too similar to my k, but small k is kappa. So kappa at a frame U is a, well, the curvature should go as a function, so it should then, I mean, I will first write it this way, so it goes from G, and it should have the values in the two forms. So what we end up with is it should be lambda 2 G mod P Joule tensor G. Right? That's how it should look like. And the way we define it is that kappa at U evaluated at xy, so I will forget the U, so kappa at some frame is a function, right? Evaluated at xy equals the big K at omega minus 1 of x, omega minus 1 at y, right? And you may ask, well, so here it might be any vector fields, so what shall we do with the quotient? But that's not a problem, because we know that whatever will be vertical will kill the curvature anyhow. So we can take any cover of a chosen element here in G, and that will be okay. But as a rule, we shall assume that we've got a split. So let's assume that we've got an identification of G mod P is identified with something I will call G minus, which is a vector subspace in G. Usually what we do is, for example, with the classical affine geometries, their reductions, or the parabolic one we heard about yesterday, so we expect to see that there will be some further structure, some nice filtering. So here the filtering was that it was G minus 1 plus G0, which was a Z grading with all the other components vanishing, right? Whereas here, in general, I can just take the G minus and don't care about brackets now, right? And choosing the component means that I identify it with G, right? This way. Right, so let's move to the bigger blackboard now. And let's compute a little bit. So actually what we shall follow tomorrow more closely and in more depth is something which I will call invariant derivative. It has got a nice geometric description. In particular, we worked on that. So several people before, and we wrote a recent paper with Andy Chubb clarifying a lot of things there. So I could have edited here. So it's a paper in honor of Sasha Vinogradov in the proceedings from the conference from 21, and it appeared very recently at AMS. Where we deal with this thing in a much more conceptual way, but for us now it will be easy to do it the following way. So I will simply take a section, gamma of say some V, and I will go to functions on G valued G minus star, or well, actually I can do it G star tensor V. Right, so these are smooth functions from G to V, and now I will do it this way, and the way how I take it is S is mapped to omega minus 1x. Well, actually, I have to write it this way. X maps to omega minus 1x acting on x. So this is a function, and this is a vector field. So I simply take the action of the vector field on the function. Right? And now, it's quite nice because if you really keep it going with the whole of G star, it's something which is called the fundamental derivative. Fundamental derivative. And you may see that this fundamental derivative, it's quite straightforward to show that actually it may be also seen as a mapping which goes from gamma V into gamma A star tensor V, and it's invariant. Right? It has got, say, beautiful content because it's something absolutely natural and it works for absolutely all Cartan connections. But it has got also quite a bit of drawback, right? Because you know that if I differentiate with respect to something vertical from the adjoint tractor, so if x was in P, then it's just some algebraic action. Nothing but that. But if I do it, so it's just messed up. So you have a lot of redundancy there. So it's not a very nice derivative, and also it doesn't look very much like doesn't remind ordinary covariant derivatives with respect to metric or an affine connection, right? Because simply this is too big. We would like to see only the G mod P star there. The disadvantage is that if you restrict to the G minus here, you can. But then, of course, you lose the invariance in general. But you can use it as tools, and the paper I mentioned with Envy is doing exactly this, just showing in which way and how much we can expect to get everything invariant out of these operations. I still have got 5 minutes to go, so let me finish with playing a little bit with the curvature function kappa. So of course, I mean, the easy thing is to compute. So I will write for this, I will write for the invariant derivative, I will write nabla x omega s, and either I will restrict x to the G minus or I will leave it general, so I don't care now, right? So it will work anyhow. So what does it mean for the invariant derivative? So what does it mean if we say, right, nabla x, nabla y? Yeah, so s goes to omega minus 1x s. So if we write the commutator, So it's clear what it is. So I will also write x tilde y and so on for the inverse vector field. So whenever I have a letter and I put a tilde on, it will be the constant vector field on the fiber bundle, right? So if I take the commutator, so it's very easy to see what it is, because it's just the commutator of these ones, right? Nothing special. And they should act on S. But now, from the structure equation, so you see in a quite straightforward way, if you just evaluate the structure equations of the, so it's d omega at x tilde y tilde plus 1/2, so it will be just omega on x tilde is xx, so it will be just the bracket xy, and that's this. So it's the kappa xy, and you see here it's quite easy to compute what it is, because omega on x tilde will be a constant function. Here also a constant function. So the only thing which remains is minus omega minus 1 of xy plus xy. So this is actually how we evaluate. No, wrong, wait. Omega minus this way, right? So should I do it right? No. Right, it's just minus omega evaluated on this. So omega evaluated this way. Right, so that's what we get. And so here we see immediately that we get omega minus 1 xy minus omega minus 1 of kappa xy acting at S. And that's exactly what we usually call the Ricci identity, right? It will be the invariant derivative in the direction of the bracket hitting S minus, and now it will be the invariant derivative in the direction of the curvature hitting the S. So it's, in the case of my example, you can imagine what happens, because the bracket is 0, so you get the commutator equals to the algebraic action of the curvature on S plus the derivative, so minus the derivative in the direction of the torsion. The torsion is 0, it's just the usual Ricci. And yeah, so I thought I would just manage one more thing, which would take more time, but I can at least write the result, and then I finish. So, right, if we evaluate the very same structure equation, so if we evaluate the very same structure equation, so I can be naughty, and I can also say that it's a homework. So you can try to evaluate the structure equation on x tilde, y tilde, z tilde. And if you do that, plus 1/2, so it will be just omega on this, so it will be bracket omega of x tilde, y tilde, z equals kappa x tilde the big K. Y tilde, C tilde. And if we just do a very simple, straightforward calculation without any effort, we get something which will be actually either differentiation in the directions of a double bracket x tilde y tilde z tilde, or a simple bracket of x, y with and z. So if we take a cyclic sum, it disappears by the Jacobi identity on vector fields or real algebras. And then there will be what remains in the so-called Bianchi identity. And it's really absolutely straightforward. So even I was able to do the computation in a few minutes. And just to have at least some lesson, some moral. So if you look at this, and if we restrict to things like this, then of course a lot of terms disappear because the brackets of x and y are 0. And what you get is the standard Bianchi identity for connections with torsion. And if you remember from childhood, so for example in Kobayashi no Mizu, it's in the second volume somewhere in the middle and it looks like very complicated theory. So just making the things algebraic enough at the level of the homogeneous bundle, and noticing that actually whatever we see at the level of the Klein model survives with some curvature contributions in this curved world, but essentially the same, saves the day and allows us to produce the elementary things, or well, not that elementary, in a really elementary way. So tomorrow I shall continue with the jets and go to the Verma modules. That's it.
Okay?
Not tomorrow, the day after.
We have short time for questions.
So maybe I shall have a question. So is it too elementary and should I speed up the day after tomorrow, or is it okay?
Please don't speed up.
I have a notation that is confusing me because K, is applied to the x tilde, the y tilde, and then to the x, y, and I'm kind of confused. Little k, big K, I'm just...
No, little k is kappa, it's the curvature function.
Yes,
and the big K is the k which comes from the structure equation.
They look very much alike, that's the point.
Yeah, well, that was my warning. The small k's will be kappas.
Okay, so if there are no more questions, you can thank the speaker again.